Okay, so we'll wait for around 2-3 minutes till you answer the questions, and then we'll move on to the next slide.
After that, if you can from rows to token, from giving publishing values like 1000 and 30, this thing should turn and that should work in token. That is interesting. After that, we have to get the SPG data and GPS data.
Okay, जो 16 जो फ्रीडम का होता है ये ओडी पूर्णा का ओडी जो फ्रीडम का ओडी लिखी पूर्णा का सिमुलेशन जैसे माता का कार्य है
that I want to
know. I know I can explain but I know that so done let us also know about the system.
I want to do for basic
basic level for the program this is also continuous, so we don't have to check the difficulty.
Doesn't matter this thing, they are putting in Hydra. Hydra will give.
Because I need 6 of freedom.
I need also 6 of freedom.
Yeah, that is similar.
I need like high fidelity simulation.
Yeah. Chances are there, but because they can also meet tomorrow at 5 p.m.
Do you have any doubts, or are you attempting the questions? I mean, if you have answers to these, you can just put them in the the messages, the chat, and then if there is any discrepancy, we will discuss. Else, we'll move on to the next step. Yeah, first one is, my voice is breaking. Oh, it might be. I'm not sure. Internet connection might be. Okay. Yeah, first one is D. So QML, as we saw in the week's lectures. No, 2 is not C. 2 is actually V. The correct sequence is that first we will have a PyTorch model or any other model. It can be if you are having a TensorFlow model or anything. They will not usually by default save it as a, or any model that you will have open source. They may not necessarily be in the ONNX format. So the first step is actually to convert any other model into ONNX format. That is the 2. Then the next step is to import this ONNX model and load it using TensorRT. So the TensorRT platform is the one that is going to do the calibration aspects of it. So once you have imported it, you can start the optimization process. So apply optimizations and generate an engine, and this engine then you can deploy it and put it on a target hardware where the inference is supposed to happen. So in fact, the engine has to be actually created on the hardware that you are going to implement. So the 2 is actually B. So in fact, I actually wanted to show a demo of this TensorRT today, but I was not able to prepare it before the class. If possible, I will record it separately and append it to this the live session later and put it on YouTube, or maybe I will either that or I will include it in the next session. So the typical steps actually include like as far as that demo was concerned, or maybe I will shift to the notes and just give a general idea. So the idea was actually to take this object detection model called YOLO V5, and this model is actually a model which is trained on a very huge data set called COCO data set. and this data set has so this has many of the usual day-to-day stuff that you see around. Like it will have classes like pers- from which part? Yeah, from YOLO V5, right? Okay, yeah. So the image that the demo that I was about going to show today, the process of that, how that goes along, I'm trying to kind of describe that. Okay. So the idea is that you have a YOLO V5 model. Now this is actually the version of it. This model that I was looking at. It is a object detection model. I'm at Chennai, Madras. Oh, okay. Are you a PhD student? Mm-hmm. Oh, nice. Oh, that's good. Feel free to ask any questions. I mean, I think since you are the only attendee today, so feel free to ask. I will answer everything that I can for you. Mm-hmm. Yeah, sure. Anytime. Yeah. So the idea of this, actually, I was not able to fully complete this demo before the session. So I will planning to actually show it in either the next session, or I will append it as a recording to this current live session. So depending on which works. Yeah, that will be good. Sure. So there is a very popular model called YOLO V5S. There are in fact variants of it. So S, M, and so on, which are like better and better versions of it. So this model is actually a object detection model. What we have here is that, so the idea of this model was actually it's trained on a data set which will have some very day-to-day images. So it will have images of cats, dogs, and very generic classes. So one of those sample data sets that are like that is one of them is called Coco dataset. So this has a huge number of classes, and all of them are like very generic objects that you see around day to day. Is it working? Oh, okay. So yeah. So then this Coco dataset objects. So our job is now, let's say there is a specific, let's say there is some glass or something in the image, and there's some person around it, let's say. So this model, this object detection model, it can specifically point out and tell you what part of the image the glass is present and what part of the image the person is present, and it will label the boxes accordingly. So that is what the model was trained on. So there is a good amount of detail about the algorithm, but we'll not go into the details of the algorithm. The idea is that so now this is an object detection model. What we want to do is, let's say you have built some small robot, okay, and you want to basically expect this robot to be able to maneuver in the, let's say, a room, and it should be able to, let's say, separate out things in the room, like let's say a chair or a person and so on. So these objects that are available in your usual room setup, they are already present in this data set. And the model that we are, this YOLO V5 model, is well capable of being, doing the detection for it. I think there is some static sound that is coming from your, yeah. Okay. Maybe if you have anything you can say, you can just text it in the chat box. Okay. So I'll just continue. If you have any doubts, you can just put it in the chat, and I will stop and recover that one. Okay. So the idea of this model is that it's going to be able to detect some day-to-day objects that you see around. But the thing is, this model is now going to do all of its computations on, let's say, FP32. So floating point 32 operations. All the weights are stored in floating point 32s. All the activations, all this model's inference is actually going to happen on FP32 level. But let's say if you have a small robot which has some camera or some LiDAR and generic sensors which are present. So this is your robot. This robot in general has to do a lot of processing of its sensors around. So even LiDAR sensors and camera sensors, they produce a lot of data, and usually the onboard computer on these devices will be very, it won't be that good like your workstation or something on which you can get a very high inference rate with on, like, so the computational resource that you have on the robot is not going to be that good in terms of its speed or something. So what you try to do is, instead of going with the so you try to essentially simplify the inference process and make it faster. And one way you can do it is by going for a lower precision operations. Okay. So what we mean by lower precision, let's say this is a floating point 32. It takes much longer to crunch the numbers for a 32 bit sized number. But if you go for an int 8, it's going to be far easier for the system to do all the computations and give you a good enough rate of the predictions. So the problem that happens is that when you are going from FP32 to int 8, your dynamic range, or the amount of variability in the numbers that you can store, that information is now has to be compressed in a much smaller amount, or much smaller variation of numbers basically. So for int 8, let's say that will be going from some minus 127 to 128, something like that. So plus 120. So what we try to do is, there is a process called calibration, which has to be actually implemented before we can actually put this this lower precision model onto our robot. Okay. So the thing is, as the previous question that we just saw in the PDF, it was asking what are the steps that you need to actually do. So TensorRT is actually one of the libraries which allow you to first do this process. So we'll note that here. Okay. So the library that allows you to convert this is called TensorRT, and what happens is that you have this FP32 model, which is, let's say, your PyTorch or from any framework that you generated the model be. And what you try to do is you first try to convert it into a ONNX format. So this is more like a generic format in which models from any different libraries can be, in a common way, they can be represented. So this ONNX format, you first convert the model, then you try to load. So you have to first so this, when you do the ONX conversion, after that point you have to load the model into TensorRT. What this is going to do is, at this point you actually, this ONX file that we talked about, it's not having any customization or optimizations already done. It just carries the same information that your FP32 model is actually carrying. But now you are supposed to put this TensorRT into the computational resource on your robot. Okay. So a typical computational could be, let's say, an NVIDIA Jetson Nano. So this is more like a small board which has quite decent amount of computation capabilities. But since there are many more sensors that you will be working with, you want to kind of reduce the amount of computation that it has to do on, let's say, images. So what we do is on this computational resource, you install this TensorRT library, and you also put this ONNX format model onto it. But you are not going to do the inferencing using this model. What this library will allow you to do is, it will basically it will simplify the model and make it more optimal for this specific hardware. Okay, and during that thing, there are several things that TensorRT actually allows you to do. One of them is actually conversion of this to int8, which is called the calibration process. So since our dynamic range, or the range in which the model weights could have been represented, that has reduced now in from FP32, which will be in the order of millions, but it has now gone to only integer numbers between a very small range. Okay, so now you have to store almost the same amount of information, but not exactly store, but you have to get the equal amount of accuracy, and but you want to get same accuracy but with accelerated computation, or accelerated computation. So once we have this ONX format and the TensorRT library, you first have to load this ONX model in the library. And what you do is, so now what you essentially try to do is, this int8 model, that variant of this model, the original model that you are trying to create, you actually pass in some of the sample data set on which sample images on which the original model was trained, let's say, or anything that is similar to it. So you can, for example, take any of open source data set like Coco dataset, and what you essentially try to do is, the predictions of this int8 simplified model or optimized model, they have to match the predictions of this original FP32 model, which is going to happen, which we have converted into this format. Okay, so that is the process of that is called the calibration. So you have to pass in some data set which is similar to their original data set, so that you can check the predictions of this FP32 model, and you can also check the predictions of this int8 model, which you are going to simultaneously update or evaluate basically. And then what you do is you create an engine out of it. So this engine is what we are actually going to put on the computational resource, and that will do the inferencing. Okay, so that is the overarching idea behind this the demo that I was planning to show. So if you have any doubts at this point, you can ask, or if it's clear, then we'll move to the next set of questions. Okay. I hope that gives at least a big picture overview of what the process is. Okay. So we'll shift to the questions. So we have covered first and second question. So first one, the answer to the first question was D, QML, and second question was the B. We'll move on to the third. Okay, sure. Actually, there are no such sample question papers in general for these exams. I mean, the assignments that you actually see in the NPTEL course every time. So most of the questions are kind of on those lines only. It's not usually different from those questions. So the assignment itself should be a good set of sample questions for the exam. Along with that, during the live sessions also, yeah, almost 90% of the questions will be, more than 90% will be from the slides only, whatever is covered in the course. Yeah. No, actually 3 is D, the Apache arrow. Yes, 4 is C, subgraphs. Okay, so we'll just quickly recap the question answers. 1 was D, QML. 2 was B. 3 was D. And 4 was C. Okay, so we'll move on to the next set. Yes, 5th is D, QDF. And Spark also we have done. I'm not aware of it actually.
That is true. Just see over the states. Also we say that it is states. So there should be.
Okay. Maybe we can check it actually online. Yes, sixth is A. It looks like SparkDF is the alternative possible, and so QDF is more ideal for a single system, single machine, but SparkDF is suited for distributed big data processing. Oh, so if the dataset is too big to fit in a single machine, SparkDF is better. Yes, 7 is also B. Yeah. So 8 is actually dusk. C, option C, dusk. So it is basically to scale from a single GPU workstation to multiple. Yes, 8 is C, dusk. Ninth is, yes, A, graph. Okay, so we have discussed the questions on this. Just to summarize, 5 is C, Courier. 6th is A, Works filter. Then 7 is B, Thrust. 8 is C, Task. 9th is CoGraph A. Okay. We'll switch to the next. Yeah, 10 is B, Rapids. Okay, sure. The recording is there, so go through. 11. Actually, 11th is more tuned towards A, CoDNN. Though QGlass is actually for linear algebra operations accelerations, but for like in general deep learning are and specific for deep learning, if you want to say, that would be CoDNN in general for different types of architectures. Yes. So 12th is B. Yeah. 13 is no. Yeah. Co-effective. Correct. B. Yes. 14 is D. Again. Boolean. So just to summarize, 10 was B rapids, 11 was A Kudian, 12 was B, 13 was co-effective B, 14th is again D Kudian. Move on to the next set.
How are the phones? Clear, that they don't like me. It doesn't increase.
Very before here.
Fifteen is not good out. 15 is day rapid. In fact, all of CUDA and UML, you can say they are more tuned towards computation, and DAL is more towards data augmentation, data loading, those options. Yes, NVIDIA Communications Collect. Yeah, B, NCCA is the correct answer. 17 is not. I mean, OpenCV is not really having anything specific for GPU acceleration. So the answer is actually C. DALI for 17. So in general, these deep learning applications which are having images, you need to kind of do some data augmentation processes before you can load the data set. So this DALI as a library, it allows you to do this processing in an accelerated environment on a GPU. Okay, so 17 is C. Yes, 18 is A, OLN. Just as we discussed in the yeah. It's like a common platform for storing models from different across different frameworks, be it PyTorch, TensorFlow. Are you sharing screen? Yeah, I'm sharing my screen. Is it not visible? I'm sharing the questions. Okay, good. No, 19 is actually C, TensorRT. In fact, that's the library we were planning to see in this. So TensorRT. So the edge devices, in the sense, the kind of devices, small devices that we put in some robots or something, or embedded devices. Nice. So the idea is that this TensorRT library will allow you to get better inference times for your machine learning models on these smaller devices. We'll move on to the next set. We actually didn't discuss 20. So, just in case, so 20 is actually rapids. C. Okay, so the idea is that pandas and numpy, though they are commonly used in data analytics and machine learning, they have no specific components that are for GPUs to make it more accelerated. Yeah, 20 is C. Correct, rapids. Is it okay if we slightly pace up the discussion of this? Okay, so what we'll do is we'll wait a little less after every question. Okay, so let's say at a time 3 questions. Okay, we'll discuss 3 questions at a time at once. So 21st is actually D, conversion. The process of converting like creating a new engine, basically a optimized engine that can be loaded onto a edge or embedded device using TensorRT. So 21 is D. 22 is A, NVML, because the other are actually different libraries, or they have different purposes. So TensorRT has the purpose of converting the models. DALI is for creating faster or optimized image loading pipelines for deep learning applications, whereas Fublas is for GPU based matrix linear algebra operations. So 22 is A, NVML. 23 exactly. So 23 is D. So that just I was describing. So in general, for most image related tasks, maybe I'll just quickly describe what it is. So usually when we try to do image any models, let's say for image processing. Yeah, I am sharing the tablet screen. Is that visible? Is my screen visible? Yeah, go ahead. Is there any doubt? Okay. You're saying yes. So the idea is that when we want to do some image processing or image related training models, we typically have, since the size of the images are big, let's say you have a bunch of images that you want to load at once, and each of the images is actually can be interpreted as a 2D array. In fact, if it's color image, it will be a 3D. The idea is that loading the entire set of images into your GPU at once is not possible. So we want to load them few at a time. That is what the batch loading is like. Right. So when we do the batch loading, we typically, so there is some pre-processing operations that you might be interested in doing on the image, let's say, which could be typically that is done in image related architectures. So in tasks such as object detection, segmentation, image segmentation tasks, all of these tasks, what we typically try to do is we'll do some augmentations or modifications to the input image, which could be somewhat, let's say, rotate the image or flip it or something like that. And so this allows the models to get a more generalized something like a more generalized view of the data set, and this additional a sort of passing of the data. That is called data augmentation. So this process is what we want to accelerate while loading. So that is what the pipeline, fastening the image processing pipeline is about. So that is what the 23rd option D DAG is. Okay. Then we'll move to the 24th. So the process of actually getting from, let's say, FP32 precision to FP16 precision, that is called quantization. So this is very commonly done to reduce the size of the models. And so let's say there is a very huge model. In fact, these large language models and their variants, they are quite huge in size. So you can't load it all in the GPU at once, your usual GPUs. So what they do is they try to compress the model so that by reducing the precision of the weights, and then it's passed for the or shared. So that process, the process of reducing the size by reducing the precision of the weights and activations, that is called quantization. Okay. So 24th is B, quantization. 25th is again 25th is again task. So task is that library we previously also saw. 26th is so the 26th is CuPy A. TensorFlow, as we know, is their framework. JAX is actually a library which is for some specific operations, like the automatic differentiation operations. So it has functionalities for accelerated computation of those, and these are commonly used for applications where we are looking at something at the intersection of scientific computations as well as on GPUs, basically. So that is where JAX is. QML, as we saw before. So the answer of 26th is A, CuPy. '27th is Horobot. So this is actually what was covered a few weeks back. So none of the others are actually very specific to model training. Okay, they are related to model, as I said, data loading or data augmentation, something similar, or computations. But moreover, is my voice is breaking. Is it okay now? I'll just repeat the answer for 27th. So 27th answer is A, Horobot, and 26th answer was also A, CuPy. Okay. And 28th is actually HDF5. So it's actually a more specific, efficient data formatting method for writing large data sets in deep learning. Our usual CSV, JSON, these are not very specific for loading fast computations on deep learning applications, but HDF5 is more specific for that. So that brings us to the end of questions for today's session. Okay. So if you have any doubts, you can ask, or maybe I will wrap up the session for today. You are free to ask next time also. So we'll wrap up today's session. Thank you for attending.